And we're live. Hey folks, Phil Zito here, and welcome to episode 21 of Smart Buildings Academy TV. And in this episode, we will be discussing control modes, specifically PID loops. We're going to look at how PID loops work. We're going to be talking through how do you tune PID loops, and we're going to look at kind of just doing PID loops on a control system. My name's Phil Zito, the founder and CEO of Smart Buildings Academy, where we help businesses and individuals increase their capabilities around building automation through online training, quantitative skills assessments, and things like this, Smart Buildings Academy TV, the podcast, as well as our blog articles. So without further ado, let's go over to the whiteboard and let's take a look at how we do PID loops. Okay, so PID loops and PID loop math and all that fun stuff. So if you've been following along, geez, this is a hard marker to open up. If you've been following along for any amount of time, then you know that we have covered on-off control, we've covered sequenced control, we've covered floating control. And during a lot of these controls, I've talked about how there's PID loops involved. Like in a sequencer, we'll take a PID loop, we'll take the output of it, and we'll feed it into the sequencer to drive the sequencer. We'll feed it into a floating controller or step controller. We'll do a variety of things, right? But we never really covered what PID loop controllers are. So PID loop stands for proportional, right, integral derivative. Now, my philosophy on this is that as a controls and building automation professional, we really should only be using P and I. And I'll talk about why in this episode a little bit later in it. But in order to understand how all this comes together, we have to understand what we're trying to do. Now, for most of our control processes, we're trying to control to a set point, right? And we're trying to control a process variable to a set point. And we're doing that through what's called a process loop. So we have a process variable and we have a set point. And I'm going to go through definitions in the beginning of this. It's really important you pay attention because there are so many people like with 20 plus years experience in our field who don't understand PID loops, and the only way they tune them is because they've memorized settings. And as soon as you stick them in a scenario where they don't have those memorized settings, they don't know what to do. So what we're going to do is we're going to look at, right, process variable, set point, and the difference, the delta between these two, that's what that triangle symbol is the delta symbol. So the difference between these two is going to be known as error. And error is going to be critical. The error is going to be what drives our integral. It's going to be what drives our proportional response. And when we do the math on this and we start to figure this out, it's going to be the single factor, the single most important factor, besides for maybe whether the loop's direct acting or reverse acting, that determines how our loop kind of performs. All right, so as I mentioned, we have P and we have I and we have D, but we have process variable and set point, and that's going to go into our PID loop controller or our PID loop logic block, and then that's going to drive an output. And this is a process loop. And there's an equation that's running inside this logic block, and it runs every half a second to every second. That's the loop, okay? And what happens is it calculates this output based on that loop. So this process loop is running. It's running every second to every half a second, just depending on your controller. And it's processing the difference between process variable and set point and determining an error and then multiplying those against your proportional factor and your integral factor. Now I'm going to teach you a very basic way to do PID loops and to do the math, and then you can kind of extrapolate upon that with whatever version of controller you're using. All right, so for proportional, the general rule is that in order to come up with a proportional band, we are going to go and we are going to take, right, we're going to take our throttle range divided by sensor span. Now, this trips up a lot of people, the sensor span portion. The throttle range is really simple. It's the range of whatever output we're driving. So if we're driving a 0 to 100% valve or a 0 to 100% fan speed, then our throttle range is going to be 100%. And most of the time, our throttle range is 100%. Like when we're using 1/3, 2/3 valves in steam control, we may have different throttle ranges, but most of the time it's 100%. Sensor span is where people get tripped up. So if I tell you that you're controlling a pressure loop, like a 1.5 inch static, right? So you've got 1.5 inch static and you're doing that and you are going and creating that sensor span and you're like, okay, what is the sensor span? Because the sensor span is the controllable range of the process variable. So what a sensor span is not, let's say we have a 0 to 5 inch static pressure sensor, and that's its capable range. Our sensor span is not 5. Our sensor span is the controllable range. So at what point would we want to hit 0, and at what point would we want to hit 100%? So you may say at 2.5 inches of static, we want to be at 0. So 2.5 inches of static, we want to be at 0% output because this is a reverse acting loop. And at 0.5 inches of static, we want to be at 100% output. So what we would do is 0.5 or 2.5 minus 0.5 would give us 2. So our sensor span is 2. Now another example of this would be like if we have temperature and we say, okay, at 72 degrees, we want to be satisfied, and at 70 degrees, we want to be 0%, and at 74 degrees, we want to be 100%. We're not having any dead band in this. This is just a simple equation here, right? And so 0 and 100, that's our range. And we look at 74 minus 70, that gives us 4, right? So that would give us 4, so we would have a proportional band, or sensor span rather, of 4. So 4 into 100 would be 25. 2 into 100 would be 50. Let's use the 25 example, right? So we got 25 for our proportional band. This is where error comes into account. You should, in theory, if you're doing things right, you should be able to get to 100% output on a PID loop just with proportional response. So if you go, let's say that we have a proportional band of 25, and we're doing that, and then we are at a set point of 72, right? And we have a process variable of 74, okay? Now, what we've got going on here, and I'm doing the math a little wonky because I actually started this at 70, so I technically should put a bias in here. So just go with me because the math's going to look a little bit wonky, and I haven't covered biases yet, but just trust me on this, please. I know the math's going to be wonky. But what would happen is that would be a 2-degree error, right? So we would get 50% output. In this equation where I had a 50% bias and I'm preloading the output with 50%, I would actually already have a preloaded 50, so 50 plus 50 would be 100. So you just got to trust me that that's how this works. The important point, though, of that is that I am fully loaded when I hit the top end of my controllable sensor span. And that's why oftentimes when you see loops that aren't reacting fast enough or are reacting too fast, most of the time it can be traced back to proportional issues. Because integral is an accumulative aspect, and we'll talk about that more in just a second. Integral accumulates, whereas proportional is a direct proportional response to deviations between process variable and set point, known as error. Okay, so is everyone with me on error and how error works? Because if you, excuse me, if you don't get error, if you don't understand error and you don't understand proportional and how those two things work, then like you're hosed. Like nothing else is going to make sense if you don't get these two things. I'm going to continue on. I'll wait for you all to comment. But anyways, so then we have integral. Now integral is an interesting factor because integral is two things. It's accumulated I, so accumulated I plus I times error. So what happens is that our accumulated I, so every time this process loop runs, if there is an error, our I factor times that error, right, that is calculated. And then that gets put into basically a holding register called accumulated I. And so over time, what will happen is that accumulated I will start to build up. That is why on some PID loops, you can go to 0 error and still have an output. That's because in order to have that accumulated I start to deprecate, to lower, you actually will have to go below. You'll have to have a negative error for that equation to work. So what happens is every time this cycle runs, that I times error, so that I value times error is going to go and be added to whatever accumulated I is. So why do we do that? The reason we do that is a proportional response can sometimes get stuck. You can have a load in a space where what happens is that with this load, right, this error, so we've got a 2-degree error, let's say, based on this, right, we're at 50%, 2 times 25, we're at 50%, and we're just not overcoming that load, right? We're just not overcoming it. People are like, we're just not able to achieve it and we're stuck, and that happens quite a bit in zone temps. It doesn't happen so much in pressure. In pressure, we have overshoot, so we'll talk about I and its effect there in being that it can help us be responsive and how we might use derivative there. I know I'm kind of talking about stuff, but that we haven't got to yet, but we'll get to that. So we're talking about accumulated I, and what that accumulated I allows us to do, especially on slow acting loops, is it gives us that little oomph to move that output up. And so what would happen is we would get kind of stuck if we looked at, like, this is 0, this is 100%. We get kind of stuck at that 50%. And then as that time continues to go on, I is an integral factor. It goes or is a time factor, integral is a time factor. It starts to slowly increase the loop. And then as the error starts to decrease, we're going to start to see it go down and up and down, and it should level out into like a fine, like, ripple. So you shouldn't have waves, you should have kind of a ripple. And that is what you want to see from your PID loop performance. Now, I will cover derivative, but I will tell you most of the time is derivative. You're not going to use it except in very fast, like sub 30-second process loops. So derivative, or really, really tight error, like really, really tight set points. So really tight sensor spans. Derivative has a downward effect, whereas I has a cumulative effect. Derivative has a downward effect. So it has a cumulative derivative plus derivative times error. And this is a negating factor. So whereas I is a positive factor, D is a negating factor. So D is going to drive it down. So when we go over and we look at the computer, which we will in just a couple seconds, I'm going to start off by doing a very basic PID loop, and we're going to do a very basic P-band, and you're going to see an instant response when I put a ramp object on the PID loop and we start to see it ramp up and down. Then when we move into integral, you're going to see, right, with integral, you're going to see that it starts to kind of go up, 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 up. And then you're going to see with D, we're going to see that it goes up, down, up, down, up, down, because they're counterbalancing one another. So I want you to understand that. Now, before I go through that, I do want to talk about bias, and I do want to talk about action. Okay, so bias, also known as startup value, I kind of hinted at it a little bit earlier. It's how you preload your PID loop controller. So for example, with a VAV box, we may want it to be preloaded to 50% at satisfied set point because we want that damper open in order to go and get that ventilation in order to satisfy ASHRAE 62.1 minimum ventilation requirements for spaces. So we preload it with a bias. Maybe we give ourselves a 25 or a 50% bias, and that's kind of what I was doing here. I did it subconsciously because just out of habit, I already preloaded with a 50% bias. But that bias just preloads the PID loop controller. Also, I want to talk about direct acting and reverse acting. Direct act, the simplest way to remember this is if you want your output to increase when process variable goes above set point, you want it to act directly. If you want it to decrease, you want your output rather to increase when process variable goes below set point, that's reverse acting. So right, so reverse acting is going to be like if you go down, you wouldn't expect it to go up, right? You notice how they're in reverse, right? Now, if you go up, you would expect it to go up. That's direct. So you see direct, up and up, going down, right? The process variable is going below set point, but yet the output's going up. That's reverse. That's the easiest way to remember direct acting and reverse acting. Okay, so we're going to move over to the computer. We're going to take a look at an example. I'll be over there in just a second. Excuse me. Alrighty, let me transition us over. Okay. There we go. All right, let's log into the station. Let's take a look. I should have one in folder 1. Let's go to Wiresheet View. Yep. Okay, let me disconnect this real quick, this ramp. And let me set my set point to 72. Zoom in a little bit because I know this can get a little small. Let me take a look at what my settings are in here. I want to give myself that proportional constant of 25. All right, I'm going to do that. I'm going to trigger the reset integral just so this is cleared out. I'm going to go in here to my ramp object. I always got to remember this. The amplitude, I want that to be 72, and then I want offset to be 4, right? That's how is that right? No. I always get these mixed up with my ramps. There we go. Perfect. So that's going to oscillate from 72. It's going to 4 up, 4 down. So there we go. Perfect. So that will simulate my zone temp for this loop. So once I hook this in here, let me make sure I have no I. Okay, I have no I. Good. All right, so I'm going to zoom in here again. I'm going to drag my control variable in here. Is this reverse acting or is this direct acting? It's direct acting. Good. All righty. And so we've got this, right? It starts to creep up. And we see, right, the direct response. We see that happening right here. And you see that direct proportional response happening, and it's following through. Now I'm going to slow this loop down just a bit. I'm going to make this amplitude a little bit smaller. And let's go down here. And what's going to happen now is, and you all are just going to have to be a little patient with me. When this controlled variable starts to tip up, we're going to, once it goes above 72, we're going to see kind of a little bit of an increase, right? And for every degree above 72, we should be seeing 25%. So every degree of error, we should see 25%. So you'll start to see that, right? So by the time we get to 72.5, we should be at 12.5. So you'll see that gradually start to creep up. And you notice how it's stepping up there. You see it's kind of every half a second. That is because of that execute time right there. Now, this isn't happening fast enough for me. It's just not working for me. So what I'm going to do is I'm going to add some integral value in here. Now, what I like to say is that you want to go, there's multiple different ways of doing the math for integral and for kind of calculating your set points. For most cases, I'll do like a 0.1 to a 0.2 for slower loops. Because you got to think about it, right? If this loop is going to take 180 seconds, I'm going to be accumulating error times 0.1 for 180 seconds. And if my error is 2, then I'm not a math person, so let's just use handy dandy calculator here. But if we look at 0.1 times 2, that's 0.2, and then we times that by 180, we're going to only accumulate 36 on top of our prop band over 180 seconds. Now, that's not exact science. There's actually going to be a little bit more than that, but not significantly more. And that's when folks are asking me, they're like, how do you figure out your I value? How do you know what you want your I value to be? Well, let's say we have a PID loop for a pressure loop. Super fast, right? Pressure loops normally react in 30 seconds. So let's say, and it's normally an error of like 0.5. So 0.5 times, let's give a setting of 1, which is what I like to use, right? So that's 0.5. Now let's times that by 30 seconds. We can see we're going to get 15% output in 30 seconds on top of probably a pretty big proportional band, because our proportional bands for PID loops on pressure loops are normally like 50. They're like 50 to 60. So 50 plus 15, I mean, that's 65 with just a partial load. That's like a partial half of a load on your PID loop, and you're already at 65% output. So that's pretty fast. So my general rule of thumb is like 1, so 0.5 to 1 for fast loops and 0.1 to 0.2 for slow loops. But you can kind of do that math that I just showed you a second ago to kind of guide through it. So what I'm going to do real quick is I'm just going to go through that math example again, because I went through it pretty quick and it's kind of important for you to understand. So here's how I did it. I looked at how long would I typically take to saturate the loop, to fully load the loop. So a space loop, maybe we're looking at 180 to 300 seconds. So I say, okay, I got 0.1, and maybe we got an error of 2 on a space temp. We're not going to get crazy big errors. So I got an error of like 2, and it's times 0.1, and then I times that by 300. I've got 60% of integral, 60% integral load in 5 minutes. Now the problem with that becomes when I have this like crazy huge I value. So I'm going to give myself a crazy huge I value here. I'm going to give myself something like super crazy. We would never do this. We would never put a 50 I loop value. But you're going to see kind of what's going to happen. I'm going to speed up the loop just a little bit here. Okay, let's go back. Let's zoom in. I mean, it's at 100%. And look, it's at 100% even though I'm going down. And this is what's called wind up. So you hear this concept of wind up. And wind up is where you have all this integral buildup. And remember, the only point at which we can start to decrease integral is when we drop below. Watch what happens now. See it starting to decrease? That is all that integral going bye-bye. That's not proportional. So if you are ever below set point on a direct acting loop and you still have output, you most likely have integral windup. That's what's going on. And you need to adjust your I value. That's what I talk to folks about when folks are like, how do I tune my loops? I go to this job site and the loop is like not performing. What do I do? Well, you first check out if you have a bias or a stup value. If you don't have a bias or a stup value, right, and you have, right, you have a proportional value and it's accurate, and you are below set point on a direct acting loop, but you still have output, that's most likely integral windup. And that tells you that you have an integral issue. As you can see right here, we're accumulating way too fast. We know that we have 25 for our proportional band, so for every degree of error, we should have 25%, but we just shot up to 100%, like super fast. We should not have that. And so that is a key sign of integral issues. Now I'm going to counterbalance this with an equally crazy derivative constant of 50. And we're going to see kind of what happens. Do you see it's blinking like a Christmas tree? That's because that integral is trying to counteract, or that derivative is trying to counteract that integral. And so this is why in most cases I will not use derivative, because if you don't get it right, you're going to have a crazy high oscillating loop. Your loop's going to go boom, 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 up, down, up, down, up, down. It's crazy. And so I try to avoid that by just 9 times out of 10, if I can get my proportional dialed in and I can get my integral dialed in, then I'm good. I don't need that derivative. If I do need the derivative, it's going to be a tiny little bump to kind of offset my integral, but I do not want to match my derivative to my integral, because by doing that, I'm actually counteracting my integral completely. Whereas integral or derivative should really be to shave the highs and the lows off of derivative. So when you peak on, or sorry, derivative should be to shave the highs and the lows off of integral. So when you peak on integral, you shave a little bit off of it with derivative. When you peak, bottom out on integral, you shave a little bit off with derivative. So it makes your reaction a little smoother. But in reality, most of us do not need to use that in our loops. All right, so with that being said, I'll answer any questions you have. Let me know. Okay, I see a lot in the chat. All right, it's Chad making some comments. All right, good stuff. Caesar says, Buenos noches. Hey, awesome, man. Buenos noches to you. My kids are always trying to speak Spanish to me, and I'm like, I'm from Texas, and I still don't know what you're saying. Hello, James, and hello, Amit. Oh, from India. Awesome. What time is it in India right now? It's like in the morning, I believe, if I remember correctly. So, hey, super awesome to have all y'all here. If I can answer any questions, I really hope this demystified PID loops. I saw some people sharing some YouTube videos, and they were like crazy science and like logarithmic algorithms, and I was like, holy crap, folks, it is not that difficult to do PID loops. It's two things. You got to figure out your prop band, and you figure out your integral value, and that's it. And maybe you add a bias. But I mean, don't overthink this stuff. Don't overthink it. Most of the time, if you're having an issue with your PID loops, your proportional band is off, your integral's off, or you got some sort of disruption to the process loop. You know, you got a valve that's leaking through or something. So you got to make sure your stuff's mechanically sound before you ever try to tune anything. But assuming everything's mechanically sound and you got your proportional band right, integral's pretty easy to tune. So, yep. Thanks for doing this, Phil. I'm a few hours down south of you. Awesome, Marshall. That's great. So you must be in Illinois land, because I'm up here in Milwaukee land. 7:55 a.m. Well, thanks for being here, Amit. That's awesome. Man, I can't believe... That's the beauty of this, right, folks? Is like, we're talking to people on the other side of the planet. I mean, who would have thought that, like, we'd be able to do that? That is really awesome. I mean, that's pretty cool. So, all right. I'll pause, see if anyone's got any questions, comments, thoughts. Let me know. Just a reminder that we are moving Wednesday live streams to noon on the weekday, on Wednesdays, because there's some folks over in Europe who just, they can't make 8 p.m. So we're going to move to noon on weekdays. Sorry, Wednesdays. But Mondays will continue to be 8 p.m. Central Time. Upcoming stuff with YouTube. Let's talk through that real quick. So SBA TV. We will be going through Network Basics 1 through 3 and BACnet Parts 1 through 3. So our next several episodes. So Marshall, we do this every Monday at 8 p.m. Central Standard Time, and every Wednesday now at noon. I believe it's noon. Yeah. 11. Sorry, every Wednesday at 11. So we're up to episode 21 now of this. Let me just transition us real quick to here. There we go. So looking at the editorial calendar, I've got Network Basics Part 1 through 3. So Wednesday, we're going to go through physical networks. We're going to talk through Ethernet. We're going to talk through stuff like that. We are going to talk on the first, which is Monday, about local area networks. We're going to talk about ARP. We're going to talk about Ethernet. Yes, James, 11 a.m. Central Standard Time on Wednesdays. And then the third, we're going to talk about networks. We're going to talk about TCP, IP, all that fun stuff. The 8th, we're going to talk about BACnet overview. Then the 10th is going to be BACnet IP, and then BACnet MSTP on the 3rd. And then we're going to do HVAC space control, psychrometrics, airside systems, pressure control, chilled water control, excuse me, hot water control, performing takeoffs, and point-to-point checkout. That's up till April 12th. The 22nd through the 29th will not be live because I will be in North Carolina on vacation. So those 3 episodes will be pre-recorded and will be scheduled as a premiere, and you'll just watch them. I'll try to hop into the chat, but no guarantees if my wife will actually let me get on the computer. So, hey Phil, what do you do to get a handle on overshooting PIDs with Steam application like valves? Okay, so we got to remember with Steam, what happens is that we get the majority of our impact with Steam in the initial 1/3 valve and in that initial like 0 to 40% opening. You're going to get, because Steam is so BTU saturated, what a lot of folks don't realize, and I'm sure, Dan, you realize this, but some folks listening may not realize this. Steam is actually like, whereas water is 212 BTUs, if I remember correctly, that can be stored up in water until it starts to convert to steam. Maybe it's 232. But Steam, once it actually does a state change to steam, it's like 983 BTUs per pound of steam, whereas water is like 1 BTU per pound per degree. So, 300 or 200 degree water, 1 pound of that would be 200 BTUs that it contains. And air, if I remember correctly, is like 0.3 BTUs per pound of air per degree. So obviously you can see Steam has much more BTUs. So how do you counteract that? What do you do with Steam? Steam is an example of where you might use derivative. You might use derivative, but you also might use a light integral value. Because what you want to do is you want to look at your proportional. So let's say you're doing DAT control or preheat control. Let's say preheat control. You're doing a 45 to 52 degree preheat control. So 7 degree sensor span. So 7 divided into 100, you can go and get your proportional value. So what I may do with that, right, is looking at 100 divided into 7, which math calculator, save me. 100 divided by 7 would be like 14. So for every degree of error, you'd get 14%. And so as long as your sensor is the type that it updates pretty fast, then you can get a fast reacting loop. And then you'll just use integral to kind of dial that in. Because remember, integral is going to have a effect on both negative error as well as positive error. So integral can start to step down your PID loop, and that should start to level it out. The thing with Steam, what a lot of folks don't realize, we're going to get our initial overshoot, and then we're going to settle in, and Steam's going to control. So what we're really trying to control with Steam is that initial overshoot. If we can slow that loop down with a good solid proportional band and a slow eye, then we're not going to shoot that open so fast. It's kind of counterintuitive. With Steam, we want a slower eye than we would want with like chilled water or hot water, because of just how many BTUs are loaded in that. We can get such an impact from such a small opening. So you're going to want kind of a slower loop, and that gives time for that process feedback, that error feedback. Does that make sense, Dan? I know I talked for a long time on that, but hopefully it does. Awesome, Marshall. That's awesome to hear that. I did IBEX schools back in Illinois for city of, oh my gosh, I forgot. Back when I used to work for Convergent. Alrighty. See what other questions we got in here. So we're going to have a lot of fun. We don't have any webinars coming up this month. We got a manager webinar that's going to be like multiple days. But yeah. Good. Yeah, Dan. So think about it this way. You're going to get most of that BTU in rush when you slightly open that valve. So the slower you can open that valve, the less you're going to overshoot. Because what most likely happened is people tune your steam valves like they're hot water valves, and you get overshoot because it reacts too fast. A lot of folks will think, oh crap, it's not going to react fast enough if I don't give it a large enough eye. But you don't want steam to react fast. You want steam to react slow. Treat it almost like a zone temperature PID loop, where you want a slow reaction. You don't want it going crazy. Alrighty then. I hope that this helped. I hope this made PID loops clear. I definitely encourage you all, if you want to dive deeper into PID loops, check out our PID loop tuning course. It will go a lot deeper into all the aspects I've discussed here. I've posted that in the chat. Feel free to check it out. It's relatively inexpensive. So I encourage you all to take a look at that. That being said, though, if you're watching this as a replay, feel free to ask questions. I would love to see that. Oh, I just saw, can you cascade control loops in the future? Can I cover cascaded control loops? Yeah, I don't see why I couldn't cover that. Yeah, we'll take a look at that. No other questions. Looks like we're solid. All right, cool. So, hey, folks, remember, if you want to get notified for these live streams, you've got to subscribe, but then you have to hit the notification bell, because YouTube is kind of funky in that it doesn't notify you unless you hit the notification bell. So subscribe, hit the notification bell, like the video. That will help a lot. Like, if you could like the video, that like super duper helps with the algorithms. Gets more people in here, and that just makes the shows more interactive. So I appreciate that. Share this with your friends. I hope you all have an awesome rest of your night. Take care of yourselves. Be safe. And as always, feel free to ask any questions you have. We're here to support you. Thanks a ton, and have an awesome rest of your night. Take care, everybody.